talk about something called autoregulation of renal blood flow. And when we talk about renal blood flow, we're describing the blood that's being delivered to the kidneys and in turn to the afferent arteriole, which will then perfuse the glomerulus, and therefore we're talking about things that are going to be directly affecting filtration at the glomerular level. So when we talk about autoregulation, the idea that the kidney is able to maintain relatively constant blood flow in different scenarios is important as a means of maintaining homeostasis. Now, as I prepare these lectures about this important topic, I find that all of the different mechanisms that are involved, although there's a general understanding of the major mechanisms, there is still some question about the specifics with regards to how they actually work. So what I want to cover with you all is a couple of the major mechanisms and the currently accepted concepts as far as how they work, but don't want to get lost too much in details. I was amused by an article I read as I was researching this, and this is a quote from the article. It says, "Renal autoregulatory capability is fascinating yet mysterious. Although it's been studied extensively, the kidney does not readily release the secrets that it utilizes for regulating renal vascular resistance and autoregulatory control." So that's what we're up against as we talk about this topic, yet I still think it's a very important one to cover, and I think that we can cover it at a level that provides useful understanding.
Now, an interesting relationship to look at is the relationship between mean arterial pressure and glomerular filtration rate. So I have listed on the x-axis the glomerular filtration rate, and I've marked off a number of 125 milliliters per minute, as this is oftentimes a commonly accepted GFR. On the x-axis, we have mean arterial pressure. Now, what we'll notice is that the glomerular filtration rate stays relatively constant over a wide range of mean arterial pressure. If you realize that normal pressure, mean arterial pressure, is around 90 or 93 millimeters of mercury, we see that although pressure increases, we're able to maintain that glomerular filtration rate at a relatively stable level. Now, there's limits to that. If we get too high, we'll see that GFR also increases, and if we get too low, we see that GFR decreases. So the question is what accounts for this relatively stable filtration rate even in the face of increased mean arterial pressure? And this takes us back to one of the concepts we learned about single unit smooth muscle and its response to stretch. So in this picture we have shown on this dial depicted a mean arterial pressure of this particular level. That's going to be forcing the blood through the arteriole and into the glomerular capillary, and that's going to result in a GFR, let's say, that's 125 milliliters per minute. Now, if we take that same system and we increase the mean arterial pressure, well, if nothing else happens here in response, then what we'll see is that increased pressure is going to result in an increased capillary hydrostatic pressure, which in turn will result in an increased glomerular filtration rate. But what we'll know is that our afferent arteriole, because it's surrounded by vascular smooth muscle, it is going to respond to this increase in mean arterial pressure. So what we know is that in response to that increased mean arterial pressure, that's going to cause that afferent arteriole to stretch, and in response, that causes that afferent arteriole to constrict. So even in the face of this increased mean arterial pressure, this increased resistance is going to keep the glomerular capillary hydrostatic pressure relatively stable and keep our GFR around 125 milliliters per minute. So this myogenic autoregulation plays an important role in keeping that glomerular filtration rate relatively constant, even in the face of an increased pressure. So again, we see this increased mean arterial pressure, which in theory might cause an increase in GFR, but as a result of stretching of that afferent arteriole and subsequent vasoconstriction, that brings the GFR back down to normal. So this is an immediate response, and it serves as a way to blunt the effects of that increased pressure on glomerular filtration rate. So although we know that this response occurs, it's felt that this probably is not the reason for long-term response to an increased in mean arterial pressure. So an additional mechanism is felt to play a key role, and that is of tubuloglomerular feedback. So if we look back at our renal corpuscle, which is the vasculature here with the glomerulus and Bowman's capsule, we'll notice that there are also some additional structures that are associated with this. Surrounding the afferent arteriole, we have our juxtaglomerular cells. These are the cells that release renin. And in this portion of the distal tubule, and at every nephron, the distal tubule is going to come back and it's going to pass right between this afferent and efferent arteriole, and there are some specialized sensory cells there called the Macula Densa. And so the combination of the juxtaglomerular cells and the Macula Densa, this is referred to as the Juxtaglomerular Apparatus. So what we'll see is that in response to an increased blood flow, as we saw with increased mean arterial pressure, we do see that initial response that we showed on the previous slide. Autoregulation immediately causes vasoconstriction of that afferent arteriole. But again, it's felt that this is probably not responsible for long-term vasoconstriction of the afferent arteriole, and it may also not completely blunt that effects. So as a result of increased pressure, although we do have the myogenic autoregulation, think of it as though it's not completely blunted, and therefore we still are going to have an increased pressure sensed by this glomerulus, which means we have an increased capillary hydrostatic pressure and some increase in glomerular filtration, and that's going to result in an increased delivery of sodium to the macula densa. If we have an increased filtrate, that'll be associated with increased amount of sodium, and so the macula densa is felt to be able to detect this increased sodium load. In response to that increased sodium load, the macula densa will release some paracrine agents, which will affect this afferent arteriole, and it will cause vasoconstriction. So the vasoconstriction, sure, is going to be contributed by the autoregulation that we discussed previously, but this release of the paracrine agent causing vasoconstriction of the afferent arteriole from the macula densa is likely to play a more important role in the long-term vasoconstriction, thereby keeping our glomerular capillary hydrostatic pressure relatively normal and therefore keeping our GFR relatively stable, even in the face of an increased mean arterial pressure. The other way we see this macula densa playing a role is in response to a decreased blood flow or decreased mean arterial pressure. So in response to a decreased mean arterial pressure, that's going to result perhaps in a decrease in filtration, which will result in decreased delivery of sodium to the macula densa. So this is what we would see on that initial graph where we saw the GFR dropping off if our pressure got too low. So as a result of the decreased delivery of sodium to the macula densa, that's again going to cause a paracrine agent to be released. It's going to have an effect on these juxtaglomerular cells, and it's going to cause those juxtaglomerular cells to release renin. So renin then is going to set off the renin-angiotensin-aldosterone system. So remember that as part of that, we're going to have angiotensin II being released. So that's going to have its various effects that we've discussed previously that's going to help to deal with a lower blood pressure. And it's also going to cause the release of aldosterone, which is going to help us retain sodium, which will help increase plasma volume, which will help again to try and offset this drop in mean arterial pressure. So those are the two different ways that we see tubuloglomerular feedback playing a role, first with increased mean arterial pressure, and second with a decreased mean arterial pressure. Now I'm going to tag on an additional sensor here on this slide, although it's not truly tubuloglomerular feedback, and that is that we appear to have some pressure receptors in the afferent arteriole, and those can sense a decrease in pressure, and that also will cause the juxtaglomerular cells to release renin. So again, there's two major functions of the juxtaglomerular apparatus. One is seen with increased sodium delivery to the macula densa, the other with decreased sodium delivery to the macula densa. In response to the increased sodium delivery, such as we see with an increase in mean arterial pressure, that's going to result in vasoconstriction of the afferent arteriole, which is going to help us to decrease or to maintain a normal capillary hydrostatic pressure in the glomerulus and help us maintain a normal glomerular filtration rate even in the face of an increased mean arterial pressure. When we have a decreased sodium delivery, as we see with a decreased mean arterial pressure, that's going to result in the macula densa signaling those juxtaglomerular cells to release renin.